What is up, guys? Welcome back. Today we're going to be looking into what is Informationsgehalt. I'm sorry if I'm kind of like weird right now. I'm just really tired. It's like 12:35 a.m. So it's like kind of late, but you get what you get. Let's just start and end this quickly. So what's Informationsgehalt? Informationsgehalt is basically how many bits we need to use to store a Zeichen, you know. Informationsgehalt eine Zeichens A, and we need to know how many bits we need per Zeichen. We need more bits for Zeichen that are less used, and we need less bits for the more used. You'll see this in an example further, further into the presentation. The units in this Informationsgehalt are bits. That means we use just bits for this. And the formula for this is HE is equals to LD 1 over P. P equals probability is not really true. It's more like P is equal to the number of repetitions we have of this said Zeichen, so to speak. So yeah, let's go ahead and begin this. We have some examples here. For example, we can see that we have our P, it's our probability in a sense, and we can see that we have A, and we have 4 characters, right? So A appears only once in the 4 characters. That's why we put 1/4. And B same, C the same, D the same. Then we put P into our LD, and then we get 2 bits. That means that to store the Zeichen A, we need 2 bits to save this, our Zeichen A. In this example, we have 4 characters. However, we have 2 repetitions per each. So that means we put 2 over 4, which is equal to 1/2 for each. And then once we put it here, we get 1 bit. Over here is the same thing. We have cool only 1 time, so it's 1/4. O 2 times, so 1/2. And L should be 1 time, actually, not 2 times. It's false. 1/4. So that's what we put it here. HC is going to be used 2 bits, and HO should be O, not C, is going to be used 1 bit to store the character O. So that, as you can see, the more we use our characters, the less bits we need because they're more important, and so to speak. So yeah, let's go ahead and continue. We have enthalpie in the Quelle. To find out how many bits we need for all of our Zeichen I, we need to do the following. So we find basically the Informationsgehalt first, and we multiply it by the amount of repetitions we have of this Zeichen, right? And then we keep on going with every single Zeichen, and then we sum this up. You'll see this soon once we keep going. Pi is the Anzahl von Zeichen I, and H is equal to Enthalpie der Quelle. Optimale codes here, they're mostly used to make, like obviously, the mostly, as we already said it before, Zeichen that are used a lot have shorter code lengths, while less used Zeichen are longer. So optimal codes try to take the average length of a word, and they try to minimize it. The minimal, like ideal length is the durchschnittliche Informationsgehalt an Alphabets. That means the Enthalpie der Quelle. That means that they ask you, hey, what's the best way what's the most optimal way to make something small? We just use Enthalpie der Quelle, which is this little function here. We can say here again, die minimale Codewortlänge ist erreicht, wenn die durchschnittliche Codewortlänge gleich der Enthalpie der Quelle ist. Das heißt L gleich Hx. Dies ist das Fano-Elias Codierungstheorem bekannt. So L is equal to this whole chimichanga. And you can see we can keep on going. Obviously, when we create optimal codes, we create trees when we're doing so, and they can be static or dynamic. Static means that the coding is fixed, and dynamic means that when we start compressing, a tree is created and then returned to the user. So let's continue and let's see the Huffman code. This is based on the greedy algorithm. It's really good for like data compression for JPEGs, PNGs, files, whatever. It doesn't use any prefixes. It has a variable code word, code word length for each of the characters, and it uses Quellencodierung. It's a Quellencodierung code, so to speak. So let's see how it works. We have this word called abracadabra, and it has different letters, right? So we count the letters and we organize them from most common to least common. And then we're gonna put them in these little boxes, and we're gonna say, okay, I'm gonna write the one with the most repetitions to the right, and the one with the less repetitions to the left. And then I'm gonna take the last two that I get, and I'm gonna sum them up. So I sum them up. As you can see, I have 1, 1. I get 2. So this I also sort it from less to most, but as you can see, it's 2, so it doesn't really change the order. So now I have to take the last two, meaning this 2 and this 2. So I have to take these two guys, sum them up, and I get a 4. So as you can see, I get a 4 now, and now it's ahead of B because it's bigger. However, our last two are still B and the 4, so we're going to sum them up, and we get a 6. And as you guys can see, we have a 6 now here, like in front of A. It's important to always organize your little boxes in regarding to how big your number is. So now we have to add 5 and 6, and we get 11. And once we get 11, we can do the following. We can write everything on the left with a 0, and everything on the right with a 1. So 0, 1, and then again 0, 1, 0, 1, and over here 0, 1. So once we want to access the code, it's quite simple. We can simply say, okay, I want to access A. I just write 0, and that's my code for A. For B, it will be 1, 0, 1, 0. And then for R, 1, 1, 1. And for example, for D and C, it's going to be 1, 1, 0, 0, and 1, 1, 0, 1. As you can see, the most used character is A, and it has the smallest code, so to speak. Now we can actually find how many bits we use. So in this case, we get the code length. So 1, 2, 3, 4, 4. We get the length of how many bits we use. And then we multiply it by the amount of Zeichen, or amount of characters we have in our text. In this case, abracadabra has 5. So it's 5 times 1 is going to be 5. Then over here it's 2. So we have 2 times 2 is going to be 4, because we use B 2 times. R, we also use it 2 times, but we have a code length of 3. So 3 times 2 is going to be 6. And this guy's going to be 4 and 4. And you sum them up, and you get 23 bits. And that's how many bits we use. And yeah. It's important to note that Huffman is not optimal. It's not always optimal, and really depends on the symbol probability. And it really, that can change at any time. So yeah, like other kind of techniques can have lower average code lengths. And yeah, it's important to note that the Huffman code is not optimal. So now we're going to go ahead and do the wrong length encoding. It's another Quellencodierung. And basically what we do is whenever we have a bunch of letters, instead of having a bunch of letters, we just condense them. And we say, okay, A, we have 3 A's, so that's it. Then B, we have 3 B's. And then C, we have 4 C's, right? We can also use the markers so as not to get confused. We can, oh, look, A, and then hashtag is like, oh, there's something there. 3, and then B, hashtag 3, and C, and so forth. Then we have the last one, which is the l'impulsif, the dictionary compression. So basically, we have this message, right? And what we want to do is we want to go from left to right, reading the message. So we have 1, and we save this 1 in our dictionary. Then we have 0, so we save this 0 in our dictionary. We have 1, which we already saved, so it doesn't really matter. And 0, we don't have a 1, 0, so we save it in the dictionary. Then we go with 1, we already have it in the dictionary, but 1, 1, we don't have it in the dictionary, so we save it again. So you keep on going like so, and you say all of the values like so. Then you're going to write your dictionary location. So you're going to write 0, 0, 1, 0, 1, 0, 0, 1, 1, just basically like a normal Wahrheitstabelle kind of thing. And from there, you're going to write your contents. So here, I'm going to write every single message, every single dictionary entry that I saved. In this case, everything that's in the comma separated. And I write it here. Once I have this, I can go here and say, okay, I have my dictionary location, and I can say that my code word is gonna be 0001 for this one, right? But look, what happens if this one should be a 10, by the way. I just forgot to add the 10. It's 10 and 10. Um, it's just this is erroneous. Ignore it. And then I'll just update the presentation once I upload it, so you guys don't have this mistake. But basically, you just go with the gist of it. You go just with 001, and over here 0 is gonna be 000. If we skip to the 11, for example, we're gonna say, hey, in this case, 001. Yeah, we're gonna write a 1 because this is the one we have in the right, but we want to put another 1, so we write 001, which is the dictionary like location for 1. Over here we have 01, so we just write 1, obviously, over here. But we have 0, so we want to write 010. Why 010? Because the dictionary location for 0 is 0, so we just 0 and 1, basically. So our core word is this. As you can see, this 1 is the character to the upper right. No, not to upper right, to the most right. So over here. If we have this one, for example, this would be an error. Well, it's not error really. It just we don't have the 10 here because I just made a mistake. But this will be a different code word. It will be like 0010, I think. But yeah, 0010, and that's why you can get this one. But yeah, that's pretty much the gist of it. It's pretty simple. If you guys don't understand it, you can just Google it on YouTube. I found a video of this Indian guy. I put it in the description below. I think he explains it a bit better than I do. So yeah, that's pretty much it for today. That's all of the things. I already added the exercises on the Google Drive, so check that out, guys. And yeah, thanks for watching, and I'll see you next time.